Going to do 5.3 now. So 5.3, solving systems and higher order equations numerically. This is going to be taking these systems that we've been solving here in Chapter 5, and we're looking at Euler's method, but not just for a single differential equation, for a system of differential equations. So just a couple of definitions and a couple of notations here. Normal form, this is just kind of writing it out the way that we've been looking at so far. A little bit differently than solving it explicitly in the last section. That wasn't normal form. That was, I don't know, just something different. But this is what we call normal form. We call this normal form because when we're using computers, most computers have this as the input for the form. So let's say we have our first variable x sub 1, and we've solved that for its derivative, and this is going to be solved for some function with the independent variable and then all of the functions that we have. So the function itself, x sub 1, and maybe there's another one, x sub 2, and this goes down to however many independent functions that we're going to have x sub n. So then the next equation in our system would just be the next derivative x sub 2, and then that is going to be equal to some combination or some function of all of those same variables. So the independent variable, my first function x sub 1, x sub 2, all the way up to x sub n. There would be m of these different equations, so there's a bunch more, and then finally we have x sub m derivative equal to some other new function x sub m, which consists of the independent variable and then all of my individual functions again. Okay, a little bit faster way of writing this, and the way that most computer programmers would write this in, would be in vector form. So we could take all m of these equations in our system and just combine them into one, just one equation, but in vector form. So this would be the vector x prime. This is looking at all the different derivatives here. That's going to be equal to our vector function. This is just the vector of all of my individual functions, f1 all the way up to f sub m. So just my vector f. And then inside of this is going to be the independent variable, and then the vector of all of the equations. So the vector of all of the equations is vector x, like that. So this is just a shorthand way of writing these m different equations up top here. Okay. So what is really cool about this, and what is nice about this, especially when we start looking at Euler's method, is that it's not just for a system of equations. This actually lets us extend higher order differential equations into the system. So just to kind of look, so even if equations are higher order, we can still write in this form. And I'll give you a quick general way of doing it. So let's say we had the mth derivative of y, of the variable t, and that we solved this for the independent variable, the function itself, the first derivative, the second derivative, all the way down to the next derivative down, m minus 1. Okay, so if we had some differential equation here with a bunch of y's, if we just got the highest order derivative on one side by itself, and then the right-hand side is anything else, so just functions of, or terms of t, terms of y itself, terms of the first, second derivative, all the way down to the derivative before the highest order. What we can do is we can define some new functions equal to some of these. I don't know if you guys have ever seen this before, this colon equals. In computer terms, this means that we are defining the function x1 to be the function y. So not just setting it equal to it, but we're creating and defining it that way. X sub 2 we would set to be the first derivative, and then all the way down, x sub m we would set to be the m minus 1 derivative. I forgot my colon. Look, I just made a big deal about talking about these colons, and I completely forgot to even put them in there. Okay. So in doing that, what this does is that it takes this just one equation of the mth order, and it splits it up into m different equations. So let's look at a quick example of this. Let's say that you're given this differential equation. So the second derivative of y is equal to negative 3t y prime minus y squared plus sine of t. So what we want to do is we want to convert into a system of equations. And to convert this into a system of equations, we're going to define our x sub 1 and x sub 2 in this case. So we already have the second derivative solved for. If the question does not have the highest derivative solved for, make sure you do that. It's already solved for, and now we just have our independent variable t, we have our original function y, and we have the first derivative, the one right below the second derivative. So we're going to set our x1 just to be the function itself, so that's the way that's always going to work. X2 we would set to be the first derivative. And then what that means for us is that this gives us a system of equations. Because if I look at x sub 1 prime, x sub 1 prime is just going to be equal to y prime, just taking the derivative of both sides. X sub 2 prime, that would be equal to the second derivative of y, but we already know what the second derivative of y is equal to. It's equal to all of this stuff up here. So x sub 2 prime would be equal to negative 3t y prime, which remember is x sub 2, minus y squared, remember y was x sub 1, so x sub 1 squared, plus sine, and then the variable t is just the variable t. So these two equations together would now be our new system. And this system is the same exact thing as this equation. We can even add in some initial conditions. So same example as before, but what if we were given the initial conditions, and let's say that these are the initial conditions that we were given. So y sub 0 equals 1, y prime of 0 is equal to 5. It's still going to be the same two equations for our system. We would just have to make sure that we write out the initial conditions the right way. So if y sub 0 is equal to 1, remember that we've set y to be our function x sub 1. So here we would just say x sub 1 at 0 is equal to 1. Same exact thing as that initial condition. All right, y prime of 0 is equal to 5, and remember we set y prime to be x sub 2. So my other initial condition would just be that x sub 2 at 0 is equal to 5. All right, so nothing too crazy there when changing over from a regular differential equation into its system. You're just defining these new variables x sub 1 and x sub 2. Now let's get into how Euler's works. So just recall Euler's method. This is the Euler's method we saw back in chapter 1, I think it was, a long time ago. The way that we had defined it is that we had our t's. The next t, you just increase the previous t by that h. All right, and then to increase the function itself, the next x value, x sub n plus 1, would be the previous x value plus that h times plugging the previous t value and the previous x value into the function, where the function, remember, was the right-hand side of the differential equation. All right, so this was just the generic Euler's method for just a regular differential equation that was only of an order of 1. So it only had the one derivative in there. Let's look now at extending Euler's method to a system. We are still going to be increasing my t, by the same amount. So the the next t value is the previous t value plus that h. That does not change. What is going to change, though, is how we look at our variables. So we still have those m different functions. So x1, x2, x3, all the way to x sub m. We need to increase each one of those by that step amount. So the way that we're going to notate this is that x sub 1, comma n plus 1. So this is function 1, and then the n plus 1 step. That is going to be the previous value of x sub 1, comma n. plus the step size times the function f sub 1 t sub n x sub 1 of n, and then all the way down. So x sub 2 sub n, x sub 3 sub n, all the way to x sub m of n. So remember this x sub m n, it's the nth function, but at the nth term, or the nth step. All right, and then this would just keep going and keep going, so there would be m of these all together. We'll just write out the last one here. So the last one would be the mth function at the n plus 1 step. That would be equal to the mth function at the nth step plus the step size times f sub m of the independent variable t sub n, the previous t value, the previous function 1 at the nth step, all the way down to my x sub m at the nth step. Now I know this notation is kind of awful, but I hope the concept is there for you. You take your t value, which is the independent variable, and you're just increasing that by that small step size. You're going to increase your first function by taking the previous value of that function and adding onto that the step size times the value of that derivative at the last step. All the way down until the mth variable. The mth variable next step is the previous step plus the step size times the value of that function at the previous step. We can shorthand this a little bit and write out what it would be in vector form. So in vector form, it's pretty much the same thing. So we're going to have the vector x, and then this is going to be the n plus 1 step of my vector x is equal to the previous value at x, so x sub n. That's going to be plus the step size times the function as a vector, inputting into that the previous step of the independent variable, and then the variable or the function values as its vector. And this is going to be at the previous step in as well. Okay, so this is what the system Euler's method is, but in vector form. So it looks a little bit nicer, but it's really just the same stuff as all here, just not quite written all out. I have one quick example that we're going to do, and hopefully I'll knock this out in just one video. So we're going to use the vectorized Euler. We're going to look at it with a step size of 0.1. Remember, you always want your step size to be small. And we're going to use this to approximate this differential equation. Y double prime plus 4y prime plus 3y is equal to 0. With initial conditions, y at 0 is equal to 1.5. Y prime at 0 is equal to negative 2.5. Now it wants us to approximate this on the interval from 0 to 1, which means that we're starting at 0 and we're going to have to do 10 steps to get from 0 to 1. We're not going to do all 10 of those steps. We might just do 1 or 2 of them. But this is how you at least get it started. I'm going to pull up the book here at the end and show you what the final answer would be. So first thing that we're going to do is that we're given a differential equation just in its regular form, and we want to recreate it into a system. So to recreate it into a system, we need to solve for that second derivative. So y prime is going to be equal to negative 4y prime minus 3y. I think I said that funny. Y double prime is equal to subtracting these over, negative 4y prime minus 3y. This is now when you want to set your x variables. X sub 1 we're just going to set to be the function y. X sub 2, sorry, I had to cut in there. I made a quick little mistake, but I fixed it. So we're setting x sub 1 to be equal to y, and x sub 2 we're going to be set to be equal to y prime. Okay, so remember that for our equations up here, for our system equations, where were they? Way at the top here. We had to have the first derivative solved for on the left-hand side to get our functions f. So we're going to need to do the same thing here. So x1 is equal to y and x2 is equal to y prime, but really I need to know what x1 prime is. x1 prime is just going to be equal to y prime. But we want to think about it as y prime because we don't want the y's in there anymore. We want to think about it what y prime is equal to in terms of the x's, which is x sub 2. Not prime, sorry, just x sub 2. And then x sub 2 prime, that we want to think of as the derivative of y prime, which is the second derivative, which we already have solved for over here. So x sub 2 prime is negative 4y prime minus 3y, but again, we don't want to think of it in terms of those y's, we want it in terms of those x's. So we're going to plug it in. Instead of a y prime here, remember y prime is just x sub 2, so this is negative 4x sub 2, and then minus 3 times y, and remember y itself is just x sub 1. Alright, so that looks kind of cluttered. I'm going to come down a little bit and rewrite that. So we're going to think about it like this. This is going to be our new system. X sub 1 prime is just equal to x sub 2. X sub 2 prime is equal to negative 4 x sub 2 minus 3 x sub 1. This is now where we want to start Euler's method. So we're going to have our first step, and our first step is just the initial step when n is equal to 0. At n equals 0, we're going to have t sub 0, which is just going to be the starting location 0. We're going to have x sub 1 at 0. That, remember, we were given as the initial conditions. X sub 1, which is y at 0, is just 1.5. So that's my starting location. X sub 2 at 0, same thing, because x sub 2 is just y prime, and we were given y prime starting position at negative 2.5. All right, now we're going to go to the next step. So if we're making steps of 0.1, then my next step is at 0.1. So we're going to have t, the next t value, which is at 0.1, of course, is just taking the previous value 0 and adding that 0.1. So just 0.1. But then we're going to be looking at my first function, x sub 1, at the step value 0.1. Remember to get this, it's the previous value of x sub 1, which is the 1.5, plus the step size, 0.1, times plugging this into the function of x sub 1 prime. Okay, so this is just going to be taking the previous value for t, x sub 1, and x sub 2, and plugging that into the first derivative of x sub 1, which is just x sub 2. So this is going to be spitting out that negative 2.5. All right, and then if you add all this up in the calculator, you get 1.25. Okay, so what I'll do here right below this is I'll just kind of write out exactly what it was that we did. So just for this x sub 1 thing that we just did. Remember, this is the previous value, x sub 1, at the 0th step, plus the step size times plugging that previous value into the x sub 1 derivative. Or you can think of that before, right, as that function f of 1, where f of 1 is what's on the right-hand side of x sub 1 prime, which is just x sub 2. So that's why we took the x sub 2 value, negative 2.5, and plugged it into here. All right, we still need to do this again, but now we need to do it for my next function, x sub 2, at the 0.1 step. This is going to be the previous value of x sub 2, which is negative 2.5, plus the step size, 0.1, times plugging the previous values for t, x1, and x2 into the right-hand side of x sub 2 prime. So this is going to be negative 4 times the previous x sub 2, negative 2.5, minus 3 times the previous x sub 1, 1.5. In the calculator, this should come out to be 1.95. All right, so just to clear up this step and to write it all out, we have our new t value, which is 0.1, We have our new x sub 1 value. This is going to be at the location 0.1. This came out to be 1.25. And then we have our x sub 2 function at the value 0.1. This one came out to be negative 1.95. So now these are my next set of points. We're going to take these points and do the same thing to get the next step, 0.2. All right, so I'm not going to plug all these in. It's just the same exact thing. Your t value is going to increase by 0.1, so now your t value is 0.2. The x sub 1 value, I guess we'll write it out just real quick. So my x sub 1 value at the next location, 0.2, is going to be the previous x sub 1 value, 1.25, plus the step size, times plugging in these into the derivative of x sub 1, which is just x sub 2. So here we're going to be multiplying this by negative 1.95. So this is going to be the value 1.055. And then you would just do the same thing for x sub 2. So x sub 2 at the next step value is the previous value, negative 1.95, plus the step size times plugging in x1 and x2 into the right-hand side of the second derivative of x sub 2 prime. Let me just pull out the book real quick. And so we only did 2 steps. Here's all 10 steps, and if nobody would do this by hand, everybody would have a computer to do this. So this would be the output then. This is, of course, what we really care about, the last line here. So we have our step size going from 0 to 1. We have our first function, x sub 1. This is the approximate value. This is what it would be exactly. And then x sub 2, this is the approximate value using Euler's method. This is what the exact value would be. So you can see that we're kind of close. I mean, it is off by a hundredth or so of a decimal, but it's close enough to be a valid way of using Euler's method to approximate higher order equations. Remember, we're not just looking at systems, right? We're looking at higher order equations that we can change into a system to then use Euler's method to solve.